So as we start to go through these, we'll go a little bit faster because we won't have to check each of the assumptions because you guys kind of have it. You have normality, which is a big one. What? Oh, sorry. I thought you were leaving for some reason. But if you want to check for normality, you'll do the same thing each time, which is the next one. So that's why I held off on that one. So let's look for normality for the next one. Let's X this out. I'll go back to the data. All right, go down to page page 5, and we're going to look at question 2. Oh no, sorry, that's another chi-square. We don't have to do that one. Go down to page 7. It's titled Practice 2. It says, look at the variable named depression. Is the data normally distributed? If not, is it kurtotic, skewed, and or any outliers? Please list any outliers. Plus, does the data set become normal if tried the log 10 transformations? So you'll probably get a question like this as well in the test, where you're just having to look at a specific variable and seeing if it's normal or not. So let's just do what it says. You go to Analyze. You go to Descriptives, and then you go to Descriptives again. And let's say that we wanted to look at, let's say instead of depression, because we don't have the same data set, we're looking at all negative affect. So you'll just pick a continuous variable that you're checking for normality and whatnot. You'll want to make sure this box is checked off, save standardized values as variables. You go to options, and you want to get all this good information. You want the mean, standard deviation, variance, range. You want kurtosis. You definitely want kurtosis and skewness. You can check off all of these, just get all the information you need. And you hit continue. And you get to go, okay? All right, so we got all these descriptives. The first thing I typically look at is skewness and kurtosis. This is going to give you good information. If you scroll down to page 8, you'll see how this is good to be written out. And the way you calculate skewness and kurtosis, or the way you work with it, is you divide the statistic by the standard error. And then this number will give you how many standard errors from the mean you are in terms of skewness or kurtosis. So if you notice on page 8, the first part is whatever that statistic is divided by standard error, and you get it what's calculated. And here in the example on your handout, you get 2.00 from the mean. And this number is more than a critical value of 1.96 in the positive direction. So you have the positive and negative direction. It could be positive 1.96 or negative 1.96. And if it's in the positive direction, 1.96, that means it's skewed to the right. It's positively skewed. And if you remember, if it's positively skewed, the hump is like on the back part. So that's how you check for skewness, to answer that part of the question. Then you also have kurtosis, which is the next one. You do the exact same thing. You check for the critical value of 1.96. In the example, it was 0.906 divided by 0.438. They got negative 2.07. So that means that it was in the negative direction skewed or kurtotic. And that means that it was Plato-Kurtic. If it was positive, if it was above 1.96, then it would be leptokurtic. And you would make sure to mention both of these things. And that's what you get from skewness and kurtosis. The next thing that you can do is you can check for specific outliers, and you can get a graph if you do things slightly differently. So you can go to, let's see, let's go back to the data. And, oh wait, skipped one thing. So you already have the z-scores now, since we checked off to save those z-scores that we got from before. So this will tell you specifically which ones are outliers. So all you have to do is you right click it, or however you can do it on your laptop, and you sort descending. And you can see which ones were above 1.96 or which ones were below negative 1.96. So let's see, we got these 3 up top. So when you're writing things out, you could say, according to the z-scores of each of the individuals, it looks like we have 3 outliers. that were above the cutoff of 1.96. And then you look below and you see if there's any outliers at the bottom, negative 1.96 below that. And it looks like we're good on that end. So it looks like we got a total of 3 outliers in Z negative affect in that DV. So we got all that. If I'm going fast, you got the recording. So that's cool.
Real quick,
Yeah.
could you just repeat what you said? You said a negative kurtosis statistic is leptokurtic or platykurtic?
Right. So if you have a number that is, so let's say you're looking at the column that's titled skewness. If you have a number that is skewed to the right, then it will be above 1.96. If you have a number that's skewed to the left, it'll be below negative 1.96. And it works the same for kurtosis. So if you do that equation, statistic divided by error, and you get a standard error that is above 1.96, then it's leptokurtic. If it's below negative 1.96, then it's flat. It's planokurtic. And you have that in your example from Rich as well, so you'll be able to see that. All right, let's move on. Well, so for the test, there's lots of different ways you can get the right answer. I think Rich also wanted to point out that you can do a graph for these. So, and you can even check the Kolmogorov and Smirnov test just to quickly check for normality. So this, I think you'll get full credit either way, but I'm going to quickly do the other way so you guys can have that just in case you prefer it. So for to check for normality, you can also do this. You go to Analyze, you go to Descriptives, and you click Explore. And let's say we did the same thing, all negative affect in the dependent list. For display, make sure it says both. You go to plots, and you make sure this box, normality plots and tests with test are checked off. And you can check off histogram if you want to. So you can talk about all this good stuff. And that's it. Go to OK. So you get your histogram. And from you guys, you can say like, oh, it looks like it's slightly positively, negatively skewed. I mean, positively skewed. And then you get your test of normality. You got your Kolmogorov-Smirnov and your Shapiro-Wilk. Both of these are telling you the same thing, but most people use Shapiro-Wilk. And for this one, you do not want it to be significant. So you could say it looks like our data was not normal based on the Shapiro-Wilk test being significant. So you can report the statistic and then say P less than 0.01. So that's another thing you can do. Let's say that they told you to transform it like in the example. That I don't know if you'll have to get that specific with the test, but it looks like in this example question you do. So let's go ahead and do that. For that, you go simply to transform, compute variable, and I'm going to hit reset on this one. So let's say that we did all negative affect, and we wanted it to be, we wanted to transform it, make it set up so that it's better. All you do is you go to whatever equation you want to do. So here we want to do log 10, which is what they told us. So you hit all on the function group, and then you go down to log 10. Let's see, where is that one? Where's log 10? There it is. So yeah, drag it up there, and you put in all negative affect inside the parentheses. So make sure that's in there. And you type in a new name for it. So let's say we're doing all negative affect. So I'll just type in all negative log 10 so we know what it looks like. Okay. And then you just rerun it. So you go to Analyze, Descriptives, you go to Explore. And since your data is probably likely already in there, you just go back to OK. So you just do it again. And let's see.
I think you ran the same one, not the new one that you transformed.
Thank you, Karis, I think, or who said that?
Yeah, Ms. Karis.
Thank you, Karis. Descriptives, explore, boom. All negative affect log 10, boom. All right. So it looks like it changed the this one a little bit, but not enough. Still significant. Let me make sure I'm looking at the right one. It looks a little different though, as you can tell, and you transform it. But here you would still report that statistic being significant for Shapiro-Wilk. So we don't see much of a change. All right, so that one's out of the way. Another one done. So now for when you're doing normality for the rest of the questions, you want to, I mean, you don't have to go as in deep detail as this. They won't want you to transform stuff. They won't want you to talk about like all of the different ways you can test for or identify specific outliers. But for the next ones, you want to say things like the assumption of independence was assumed. And if you're looking at one dependent variable, you go ahead, you can check the Shapiro-Wilk for it. You could say the Shapiro-Wilk was checked for so-and-so variable. And the Shapiro-Wilk was not found to be significant. Therefore, the assumption of normality was assumed as well. And whatever other assumptions go with it, you can quickly mention those as you're doing the next analysis. So you can see if you get a good system for doing each of these analyses, you can just be able to go forward with whatever you're doing. So you'll kind of see in the next example as well. So on your example paper I gave you, zoom down to page 17. You'll likely get a correlation question. So it should be titled Practice 3. So for correlation analysis, let's say they ask you to run a correlation between two variables and just talk about what is significant, what is not significant, or things like that. So let's say they actually do a correlation analysis. For this, you go to Analyze.
Wait, Jay, sorry, I don't want to cut you off.
Yeah,
but real quick, I think you forgot to, with the check for outliers, normally they'll give them a bigger data set too for the test. So it'll ask you for your opinion on what you think you should do with regards to those outliers. And I know last year what we were advised is just say like you're just gonna kick them out.
Or replace them with the mean.
Justify that you have a large enough data set.
Or you can like shepherdize or
Windsordize.
Yeah.
Thank you. Yeah, perfect. If they ask you that, or if you want to add that just to have extra stuff you mentioned, that's really good. They'll love that. Mention that you either threw them out, what you did with the outliers, you threw them out, or you shepherdized them, and replacing with the mean is also a good option as well that you can use, as long as you just mention it.
And I'll say too that, you know, if you're feeling like, I don't know if this should be included or not, just include it. Like, don't overdo it by any means, but if you're like, oh, this would add extra information about assumptions, this would tell us more about what we should do next. My experience, it helped me do really well in the exam just by putting additional information, just so they knew what I would do if there was like that situation like Renee said.
Right. Thank you, guys.
To clarify, do we run the analysis as is and we don't remove or shepherdize, or do we just like talk about it? Like, I just want to clarity.
Just talk about it. Just talk about it.
Just talk about it, but run the data as the data is.
Yep.
Because you're turning in a document that's written like results. You're not going to turn in your SPSS.
Exactly. All right. So next, correlation. Great stuff. So let's say they tell you to run a correlation between all positive affect and all negative affect. The first thing you do is go to Analyze, you go to Correlate, you click Bivariate. As you can see, I've run this already in preparation. So these two are selected. You'll probably expect some kind of negative correlation because you got positive and negative. What you want to check off, you want to get your Pearson correlation coefficients. And I believe, yeah, you want to get your means and standard deviations because you'll mention that as you talk about what you got. Your cross product deviations and covariances. Click continue. And that's all you need. Click OK. So you say a correlation analysis was run on all positive affect scale and all negative affect scale. and you talk about whether there was significance or not. So all you have to do is look here, all positive affect and all negative scale, you would say there was a significant negative correlation between the two, and you would mention the statistic, and you would say the p-value was less than what or what. And so here you got less than negative, you got less than 0.01. Sorry, I had a brain fart for a second. I lost myself. I was like, what is going on?
0.05, you mean?
Was that?
You said 0.01?
Yeah, 0.001. And you put the statistic. So here you're only working with 2, and you got your Pearson correlation, you mentioned all that. And then you could just say what the mean and standard deviation was for each. So in your example, you have exactly what we just mentioned here. It's really quick. You say what was run. You talk about the assumptions. So if you want to, you can go to check for assumptions. All you do is you run just like we did before. You can hit Explore. You can run Shapiro and Wilk on each of the dependent variables to see if normality was, you can check those histograms and whatnot. And then after that, you just talk about independence was already assumed. And let's see, if you want to talk about outliers, you can look into that as well. So you just do the same thing when you're checking for outliers and things like that. You okay? What's up?
I don't know if you have to do that for a correlation.
Well, I mean, you always want to see if your data is like normal and stuff, so you can check and go to, run and check for normality and stuff. Independence observations, normality, and all that good stuff. You can check your histogram and whatnot. But yeah. Then when you're talking about descriptives, there's also an outline for that. So you say the descriptives for the correlation analysis are as follows. You could say the first variable, all positive affect, mean equals 24.42, standard deviation, whatever that is. You can even mention the sample size if you want to get extra fancy with it. But all you're doing here is really simple. You're just talking about what you got. And you could say at the end if you would like, as so-and-so increased this decrease. So for the all positive and negative affect scale, you'd say something like, there was a negative significant correlation between these two variables. As all positive affect increase, all negative affect decrease. So you got that there. There's not so much you can really go into with these, and you have in your example exactly how you write this up. So you're all set with that
Good job.
one. Who said that?
Happy Tuesday.
Oh, it's Katarina.
Whoop, whoop.
Oh man,
Hello,
Katarina.
everybody.
It's good to see you.
Good
All
to
right.
see you too. Yeah, so I think you're doing great. I mean, I joined a few minutes ago, but you're on it.
Hey.
Well, hi and nice to meet you to all of you that I never met. Yeah, so I have to jump in a meeting for work with this space, but yeah, how's it going?
It's going good. We jumped into it. We're already down to practice question 4, I believe. And all this is being recorded, so they'll be able to use it.
Excellent.
And
Excellent.
feel free to jump in and say, Jacob, do this, tell them this instead, or anything at any moment. We've been getting some good stuff, so.
No, I'm sure you're doing, and you'll do great. No, just I guess, yeah, it's so weird because I'm speaking to people I don't know. But anyway, Rich.
You know me.
Oh my goodness,
Vera.
this Rich. Oh my goodness.
That's right.
Hi.
Hi.
Sorry, I'm interrupting the comp review. Like,
No, but
Oh,
Zoom
we-
me one of these days. We're crying out loud.
hi, happy
Hi.
Tuesday.
Right.
Yeah, it sounds like you're doing well, guys. So keep
Great.
up
No,
the
believe
good
it.
work. I don't think
watching.
you need me for sure.
Katarina is famous, you guys. So
Yes, we're in the presence of a doctor.
Helped us so much last year.
She's gonna make sure I'm giving you
Oh,
guys.
hi.
Hello. I'm
Hello,
learning how
hello.
to teach this too with Jacob, so we're trying to get to the level you're at, Katarina.
I don't know.
And A2.
That
All
was definitely an interesting session we had, or a couple, I don't remember. But yeah, I guess, yeah, I have a few minutes. In general, I'd say for all the questions, to those of you who are taking the test, my advice is simply to go step by step and to keep it very straightforward. Start, first of all, clean your data and check your data set for missing values, for 99 values, and make sure that your variables and your data set is ready to go before you start anything. And then tackle each question, one at a time, focus on, assumptions first, mention them all, means, standard deviations, and then the main results, and make sure that you know how to report them APA style, and you're good to go. There's really not much more.
Yeah. And I was letting them know that they would mention these things if there was, for example, problems with outliers and or missing data. So if you had like missing data, for example, you would say so-and-so was, there was this many missing cases, and they would like it. But they don't have to go into the analysis and have everything.
Right.
But it's,
So keep it straightforward, address everything, step by step. It's kind of like the same outline for each answer. So assumptions, outliers, and missing values if that was the case, and the results, and that's pretty much it. You don't need to interpret anything. I think the only thing different that you might be asked to do is to name factors in a factor analysis, but that's the only thing that would really change across the questions. And that's it. I did my part. Hey.
you gotta go?
No, I still have a few minutes.
All right, cool. You get to watch me work then.
Then I'll be here watching you.
All right. Cool. Everybody go down to page 18 of the practice things I gave you. There's going to be a question. It says, use the variables named Q1 to Q9. They'll probably have actual questions on the test with different like meanings to the questions, like do you prefer this or that? And it says run an exploratory factor analysis, which is also known as principal component analysis with rotation. Discuss KMO and Bartlett's test, communalities, eigenvalues, rotated matrix, and other relevant information for the EFA. And then at the end, don't miss this, discuss the reliability of new factors using the coefficients alpha, convex alpha for internal consistency. So we'll make sure to do that right at the end as well. All right, so when you're doing factor analysis, you go down to dimension reduction, and you go to factor. So I added some questions in here, Q1 through Q9 through Q10, just to make up some stuff. It's not really meaningful data, so just use it as an example of what we'll look at. So first thing you go to, you make sure you got all your variables in there. You go to descriptives. You want to make sure you definitely want your KMO and Bartlett's test. That's one of the assumptions you want to talk about. You want your determinant, want your significant levels, your coefficients, and your univariate descriptives. You go to extraction, and I don't know if they'll do this, but if they tell you guys to keep a certain amount of eigenvalues greater than keep anything greater than a certain number of eigenvalue, you can mark that right here. So let's say keep all factors above an eigenvalue of 2, which is pretty high. You would just change this to a 2, but the general rule is that you keep this at a 1. So just keep that there. If they tell you that they want you to just extract a certain amount of factors, you can go here and put how many factors you want them to extract specifically. So you probably won't see that, but that is also a possibility. So I would go with this based on eigenvalues greater than 1 unless they say otherwise. You display your scree plot. You don't have to see your unrotated factor solution. You just really want to look at the rotated one. And you go to continue. Rotation. If they tell you to use a specific rotation, go with the rotation they tell you to use. Don't ignore them. Just do it. If they tell you to do nothing else or anything, you're just looking at something different, really different, between your items or anything like that, just go, I would say go with Varimax rotation. Likely, that's typically the one that's used when you're looking for differences, just like we learned in class. So I don't think they'll trip you up with asking a specific rotation and not telling you specifically which one to use, but I usually go with Varimax because they're usually looking for differences in categories and whatnot. So click continue. That stays the same. If they tell you to suppress certain coefficients, so if you're getting coefficients stable at the end and they're telling you you don't want coefficients that are below, you don't want values that are below 0.3, you could mention 0.3 right there. So that's basically just saying once you get your output and you're looking at your coefficients table, do you want to have to deal with looking at correlations that were below that value that's mentioned right there? You don't have to worry about that too much unless they mention it specifically. Go ahead and do it. We don't have to do that. And that's all. So you click OK. So you got your factor analysis. First thing we could talk about with the factor analysis are the assumptions. So you could say prior to running the analysis, the assumptions of a factor analysis were done. We don't know about independence. All you say is independence of observations was assumed. Then you also might want to look into whether this was an adequate sample. So if you remember from your last test or the test before that, you want to make sure a lot of these correlations are above 0.3 for sampling adequacy. Most of the time, if you're just reporting for the comp exam, you go straight down to your KMO and Bartlett's test, historicity. So you could say, according to the KMO test, the sampling, the KMO statistic was 0.718, and you would say that this is good. So you would say met the assumption of sampling adequacy because it was above this number. The cutoff is 0.7. Then you also look at your Bartlett's test of sphericity, which tests the assumption that this is an identity matrix, and you want this to be significant as well. So you also look at that. So we also have this written out. So don't worry if I'm saying these really fast. So check out your handout, and you could check out and see where it talks about the KMO and Bartlett's test and just how to write those out specifically as you're doing your test. So you have a lot of practice and a lot of time to write those out. Let's see what else. And let's see, am I missing any assumptions to talk about? All right, so let's talk about what we actually got. So when running the analysis, they might ask you a lot of different things, like how many factors do you want to extract and all the other good stuff. For this, it's good to go to your total variance explain table and see what you got. So let's say they ask you which one contributed the most variance. You always look at this top one. So you would say, look, you could start off by saying something like this. According to the total variance explain table, a total of 3 factors were extracted based on the Kaiser's rule of taking out, the eigenvalues above 1. And you could say with the greatest amount of variance being accounted for by the first component. And then you can mention the exact amount of variance that this one contributed. So it all depends on what they ask, but likely you'll just write about what you see. This one took out 33.098% of the variance. Component 2 did this, component 3 did that. The next thing you check out, you can back this up with your scree plot. And you could say something like, so based on our table of our eigenvalue rule, we kept 3. Just like that, you look at your scree plot, you could back this up by saying, according to the scree plot, the point of inflection was at 3, which also supported our reasoning for taking out 3 components. Specifically, you'll also want to talk about what the components mean. So you'll go to the rotated component matrix. And this is where you'll talk about what these components actually came out to be. So for component 1, component 2, and component 3, you want to see where the heaviest loadings were, and you want to talk about what they mean. So let's say that component 1, based on the way it's set up, we have the highest loadings for question, oh, that's fine. Question 3, 1, 8, 5, and 2 appear to load on pretty high to component 1. So based on what these say, let's say that question 3, 1, 8, 5, and 2 all mention like aggressive styles of parenting. So like said like punish child by grounding them, punish child by doing this and all this other stuff. And that's a bad example, but let's just go with it. So you would say component 1 might be aggressive styles of parenting. And then let's say the ones that loaded high onto component 2, question, let's see, question 9, 6, and 7 appear to load the highest on that one. That's like nice styles of parenting or something like that. Again, this data is made up and it's set up so that it's not quite, meaningful. So you probably might not find really good stuff with this. And then 3 looks like question 4 and 10 might have loaded onto that one. Let's say that's neutral styles of parenting. You would come up with these names yourself when you're trying to lay out what each of these things are to be called. And if you go down to the bottom of page 18 and you look at these, this is an example of how you would talk about each of these things. So first you would go to the total variance explained table and say what each of these components mean based on how much variance they extracted. So you would say, according to the total variance explained table, factor 1 or component 1 accounted for 60.2% of the variance or whatever variance we see on our table. It had an eigenvalue of blank. So here factor 1 or component 1 had an eigenvalue of 3.310. And I think a good way to talk about what things loaded onto them, you could say with the following loadings, and you could put like a colon or something. And you could say what each of these questions are. So you could say question 3 was this with a loading of 0.868, question 1 with the loading of 0.806. And then once you list all the ones that had the highest loading, then you would go on to say this factor can be best categorized as, we said, aggressive parenting. This example of how to write these out is, again, written out on the handout I gave you guys. So you would go on to do the same thing for each of these components. Rich, you still there?
Yes, yes, yes.
Do you think they have to go in that much depth when talking about the components, or do you think I'm going too detailed? Or were you?
Don't worry about the components. Yeah.
Oh, okay.
Just remember the important things. A loading is a correlation. So the stronger the loading, the stronger correlation from an individual item to the newly formed umbrella term that we call a latent variable or a construct variable. And when it comes to assumptions, there are very few assumptions for a factor analysis because it's not a test, okay? So, but the main thing is your sample size. You're supposed to have anywhere between 10 and 20 respondents per item. That or per factor analysis, new factor. So, but again, yeah, don't go into too much detail about the actual loading unless 1 or 2 of the items doesn't load up well. Just say this item, the question number 23 did not load up well, therefore you're not going to use it.
Right. Or if there's too much redundancy across items.
Correct, right. And it'll tell you. So, all right,
Okay.
I'm going back.
That was it. Okay, people. Well, Jacob, you're doing a great job. I'm very proud of you. Thank you for taking over for me.
I got you.
And yeah, good luck on the test, guys. And yeah, just go confident. It's gonna be very straightforward. Follow the directions that Jacob is giving you and you'll be totally fine. You're in good hands.
Thank you, Katerina.
You're very welcome. Yeah, sorry if I cannot stay longer, but I have a very fun meeting to jump into.
No, I'm glad you popped in.
One of my psychopaths need me. So people, enjoy the rest of your night or the day. I don't know what time. Yeah, the day, evening. And good luck on the test. And yeah, maybe next time it'll be a fun meeting that we can all attend and enjoy. Maybe introduce each other. Okay.
Right.
Quarantine.
Yeah. Dante, don't touch anybody, and I will email you soon.
All right. I think I'll email you sooner.
All right. Ciao, Bella.
Right. Ciao.
Ciao.
Cool. So one thing I forgot to mention about this was the sample size thing. So check out the analysis in, which is listed on the descriptive statistics. Here we wanted, we got a total of 10 questions, and we, according to what you're saying, Rich, we probably need a bigger sample for this list of this data I've made up.
You get what you get. You know, you're always going to be lacking. So
You get what you get. Just
you
right
get
out.
what you get. Yeah. So.
All right. That's your taste of factor analysis. Practice 5, go down to page 19. They might ask you to do some sort of t-test. The example that I saw given by Rich was a one sample t-test that we could look into. And those are pretty quick as well. You just want to check for the assumptions of normality. You want to also assume independence just like usual. So you can run you go to analyze, you go to explore, descriptives, explore, just like we did at the beginning. So if you want to see how to do the normality, once again, you just check out the beginning of this video. But if not, you're good. So you check for normality, you check for independence, but you can't. So you say independence was assumed. And then you run your t-test. You go to compare means. And it's likely they won't make it too complicated about which t-test you need to do. If it's a paired t-test, they'll likely say, compare the means between time 1 and time 2 on something. There's an example of a paired t-test close to the bottom of the document I sent you guys if you want to practice that. Independent samples t-test, you're going to be comparing across some group. And they'll probably just say what kind of t-test they want you to do. So let's just do the one sample t-test and go through that. So one sample t-test. Let's do the same variable, all negative affect, and
That's one you were comparing to the norm, right?
Right. You're just comparing this one to the norm. You just hit OK. And let me move your faces out of the way. And for this one, you just check to see if the t is big and if it's significant. And you see the mean difference based on what you had from before, and based on what you had from the population to the mean, from your sample mean, So you have your example of how to write these out. You just would say a one sample t-test was conducted on to examine whatever difference that they want you to. In the example Rich gave us, it was the difference between a sample of 20 people's weight and a norm of weight of 278 pounds. So they'll have that listed for you, what the norm weight was and all that. And you just talk about what you got. So in our example, we would just say there was a significant difference based on the critical alpha of 0.05 between the mean sample weight, whatever they have set up at the sample weight up here. And then you say and the stated norm weight. And you would say T, parentheses, you'll put the degrees of freedom, equals whatever the T statistic is. And here the significance is all the way low, so you would say P less than 0.001. And here's something if you want to get fancy. I don't know if they'll ask you guys to write out the effect size, but if you're calculating effect size, they don't give you the actual effect size here. So you would actually have to calculate it. So all you would need to do is take the standard deviation that they give you, and you would have that number divide. You would do the mean. You'll take the mean difference and you divide that by the standard deviation, and then that'll give you the effect size. You guys probably won't have to do that. But that's if you have extra time, you're done with the test, you're like, I want to dazzle these people. You just do that. You got your Cohen's D.
Can I chirp in? Yeah, that's Cohen's D. You guys know the difference between a one-tailed test of significance and a two-tailed test of significance? It's only used for the t-tests.
Cohen's D is only used for the t-test. Is that what you said, Rich?
Yeah. Well, yeah, Cohen's D is only used for the t-test, but a one-tailed test or a two-tailed test, you guys know what the difference is?
It's whether we're assuming one is bigger than the other, right?
That's it exactly. If you think one side is going to be bigger or smaller than the other one, that makes it a one sample t-test. The bad news is SPSS only does 2 sample t-tests, but all you got to do is divide that 2 sample sig value by 2, and it gives you the 1 sample or the one-tailed t-test p-value.
Do we need that?
Yeah, if you are doing a one sample or a one-tailed t-test where you pick one side that you think is going to be bigger or smaller than the other side, that makes it a one-tailed test. To find the p-value to that, you run a regular 2-tailed test in SPSS, and whatever that sig value is, simply divide that by 2.
Thank you. Thank you.
No problem. I'm going back into my hole.
Cool. All right. The next one is going to be probably the biggest one. Mixed design. So go down to page 21. Practice 6. Here they're doing training 1, training 2, training 3, training 4, and a between groups variable being city, and running a factorial mixed ANOVA to determine different effectiveness of the trainings and also whether city as a variable played a big role. So if you're following the example used on the handout I gave you, just that's what those are for. But here we're going to use our own example. So the main thing you need to remember about these tests is what are the steps. So for this one, first you're checking to see if there was an interaction. And the reason you check for that first is because if there is an interaction, that means the main effects could be misleading. So you don't interpret the main effects. And the biggest thing about checking out interactions, when there is an interaction present, the next step is to check out the simple effects. So you want to be able to check all that out and be able to say, if you get the test, it looks like there was no significant interaction, so we did not look into the, it looks like that there was no interaction, so we looked at the main effects, and we did not look at further into simple effects and all that stuff. If there isn't a significant interaction, you would say, you just mentioned that, and you would like that. So let's go ahead and do our own example of that. So here you go to Analyze. You go to General Linear Model. And you just click Repeated Measures. Because it's a mixed design, one of the designs is going to be within group. So we need to have one repeated measure. So I'm going to hit reset for this one so we can see, because the process of getting your mixed design is a little tricky sometimes. So let's say in this example, we're looking at how people's positive affect change from month to month. So I'm going to put time as the within subject factor name. And I put 3 levels for this one. So that's where you put the amount of levels. So let's say they have before, during, and after something. So that's where you put your number of levels. So we add that there. Then you hit define. And this is where you turn into a mixed design, because you got between subject factors and you got within subject factors. So I set it up. So I've got cool stuff here. Positive affect month 1, positive affect month 2, and then positive affect final. So we're looking at how people's affect changed. And then you want a between subjects factor. So what could be our between? Let's say it's whether they were included or excluded. So you pop that in your between subjects. And then you just want to make sure you got everything you need. So you go to,
Plots.
I don't think we need nothing in that.
Plots.
Plots, thank you, Renee. And you want to look at condition, which is inclusion, exclusion, by the time. You want to add that there. So you got your plots for that.
Does it matter which way you enter that?
Nope. Just put them in there and they'll show you for an interaction later on. Postdoc test, you want to look for least significant differences, LSD. Continue. Estimated means, condition.
That's the only one you're supposed to select?
Was that?
When you selected least significant differences, wasn't there a few others you're supposed to check?
I usually just do the least significant differences. I don't know, does anybody typically do anything else?
It depends. If your sample size is unequal, you go with LST. If your sample size is equal across different levels of your IV, then Tukey is the best one if you have equal sample sizes and stuff like that. But, you know, with
Nice.
LST, you can't go wrong.
Nice. Write that down. Write that down. Oh, we got it on recording. Good, good. See, that's good stuff. And you want to look at your means, right? So the means for each of your variables, both within and between, and then you want to look at your interaction. Compare main effects. Save. You want to save your standardized residuals and your unstandardized predicted values and your Cook's distance. That's an assumption that you could talk about. Options, this is a big one. Boom, you want to get your descriptives. You want to get your effect size so you can talk about that in your interpretation, your observed power. You definitely want to make sure you don't miss your homogeneity test. So you can talk about those, residual plot, and that's it. Okay, hit okay. All right, and we got our work cut out for us for this one.
Sure.
All right, so let's see where it starts. So it's intimidating at first, but we'll get it set. So here you got your between subjects. This is the inclusion exclusion. Just keep that in mind. And you got your within subjects. So within is always time. Between is always just inclusion exclusion. And you got your descriptives for means and standard deviations. So when you're talking about your assumptions, you would start by saying the assumption of independence was assumed again. I know this is repetitive, but you want to do it for each one. That's how the comps work. And then you got your boxes tested equality of covariance matrices. For this one, you could actually just write out what it says here if you want. You could say the test of that the observed covariance matrices of the dependent variables were equal across all groups. Were you would either accept or reject. Here you want this to not be significant. So if it's not significant, you can go ahead and write out according to the boxes test of equality of variances of covariance matrices. The observed covariance matrices of the dependent variables were equal across all groups, and this assumption was not violated. Then you can also talk about Multivariate test of sphericity. You can say Multivariate test of sphericity was also observed, and for this one, you also want it to be, this is for your within subjects thing. Thank you. You want this one to be not significant. We just made it, so you can go ahead. Oh, crap. Yeah, that's a statistic. Good. Thank you. This one is significant, so it's violated. So then you go ahead and choose which transformation test you want to go into. So a lot of people like to use greenhouse geyser because if it's a good statistic and it works, it's good because it's conservative. So you can say in your analyses, the greenhouse geyser was utilized as for within subject effects, because that's where you utilize it right here, as the assumption of multi-test of sphericity was violated. So you can also mention that when you're talking about assumptions. And if you go into main effects for these, then you can talk about your Levine's test of equality of variances. We also know that we want these to be non-significant. So just like Mulchi's test of sphericity, you could talk about each of these. And if you have a lot of time, which I would maybe go back to this if you want to, but you could do like the F max if you want, if something is really violated really bad. F max is the highest standard deviation or the highest variance divided by the lowest variance. And you get variance by squaring the standard deviations, just like we talked about your last test. So just keep that in mind. So those are the assumptions that we start off with. Now let's jump into what we actually got. So multivariate test. So you can say according to, this is just taking all things together, according to, so you got time up here and then you got time by condition. You can start by seeing that, you know, time, the effective time was significant across all of these. If you remember, we have the p-lies trace, Wilks lambda. If you get a lot of assumption that's violated, I would report the p-lies trace. They'll like that because then you can also go to say like p-lies trace was utilized as it is a robust multivariate test. Wilks lambda, if you know everything's just all good and gravy, and yeah. So then you just report that. So you could say it appeared that according to multivariate test, that time had a significant effect on whatever outcome measure you're looking at. Then time by condition, you could say according to the interaction effect, there's also a significant interaction between time and condition on the whatever the DV is, and you just report the same statistic. And you talk about the significance. For this, you would mention the F value. You would talk about you would mention 2,58 for your degrees of freedom within that parentheses. You'll have that in your example as well that I gave you. And then you also mention your partial eta squared, which is, you talk about whether that is the variance, the effect size, yeah, thank you. And you can just have all that. The observed effect was ... All right, cool. Then you move down to, so here it looks like we got a significant interaction. So you would say the main effects were not taken into consideration or are to be considered with caution. That might be a better word, as the main effects may be misleading due to the significant interaction. So then you go down to the test of within subjects effects. Let me see. And then you could talk about, but depending on which one you use, that's the one you mentioned. So let's say time by condition, the multi-test historicity was violated. Talk about, this is where you talk about the assumption that you went with. So did you use greenhouse geyser? You mentioned that when you're talking about the time by condition interaction. If there was no significant interaction, and you want to look at your between subject effects, this is where you see those here. We only had one group, which was condition. So you could say your between groups for condition was, you had an F of this, significance of is really high, so you don't, it's not really a main effect, a significant main effect. And you would just mention like you do before, you would put the degrees of freedom, the F statistic, and you would just worry about those, and you wouldn't go on to talk about simple effects. But in this case, we do have a significant interaction, so we will talk about simple effects. So here you got your pairwise comparisons, and you can see just for inclusion, exclusion condition, you can see what's going on there. You got your pairwise comparisons for time, but what we need at this point is to see a simple effect. We don't want to just look at time, and we don't want to just look at condition. We want to look at both at the same time. We want to look at inclusion or exclusion condition by time. And this is where you see that here. You got your means for each and your standard deviations or your standard errors for each of these. And you'll talk about each of these as you're writing out what you actually got. So let's say you want to know exactly where the direction was and where the significant simple effect was. At this point, in order to know that in terms of significant, we'll have to do a split file. So I'll quickly do that. For split file, all you have to do is go to data, split file, make sure to click compare means. And if we believe there is a simple effect due to the time condition, we would then plug in the other one. So inclusion or exclusion in this case. So we can see across time what's going on. So then you hit OK. And then you run the analysis. And once again, so you go to analyze, general linear model, repeated measures. You don't have to change anything. You just go click define. Everything's all set in there. You hit OK. And SPSS loads. Go all the way to the bottom. All this stuff. And you got your multivariate, oh, it's here. Pairwise comparisons. And now you can see your simple effects. So this is where the money is right here. So you look for where you see a lot of significance. So it looks like time 3 specifically, across these 2 times, you see some significance. We don't see any significance down here. So this is where the simple effects are appears. So in the simple effect for other these might be repetitive, but just notice that 1 and 3 significant, 2 and 3 significant. So it's mainly if you want to save time, you just look at where all the significance is, and all you have to do is look at time 3 to see that. So based on the analysis, you would say something like, there was a significant simple effect of the group at time 3. So you would then say that it appeared that individuals in the inclusion group at time 3 there appeared to be a significant difference in whatever the outcome variable was. So here it's all negative affect, I believe still. But here, this is where you get to see exactly what's going on. And if you look at the example, they have a really in-depth setup with city and training. So if you want to look at how he writes out a good example of a simple effect, you would go there. And that's on page 27. And it looks like the way he wrote it out, you just say mostly which one showed the greatest increase. So kind of like we're doing here. So it looks like we see the greatest difference at time 3 in the inclusion condition. So that's how you'll talk about those simple effects. Okay. Now, we're going, we're 15 minutes over. But that's all right, we're on the last one. So let me move this out of the way. Last thing we'll do is go down to page 28, where it says practice 7. Here they want you to look at a multiple regression. So they'll just outright say it. We want to look at these predictors and how they predict a certain outcome. And you'll discuss, R squared and just regular R and all that good stuff. So for this one, you go to Analyze, you go to Regression, you hit a linear. And let's say we wanted to check out, this is just like for your comp. So this example might look a little familiar because we didn't have to change much. So all toss frequency, let's say that's the dependent variable. All the independent variables are all negative affect, all feelings of being ignored, all positive affect scale, whatever. So you got your independent predictors and your dependent variable. You go to statistics. You want to make sure you got your estimates, descriptives, model fit, R squared change if they ask for it, part and partial correlations, collinear diagnostics. Gerben Watson here to talk about independence. Now we can actually go to a statistic where we can talk about independence. Case-wise diagnostics.
That shows you if you have any outliers that are above 3 standard deviations. And it always comes at the very end of the output.
Thank you. Yeah, I didn't. That's very helpful too.
That's something that I like, but keyboards didn't really like it.
Yeah, I think it's really useful because then it gives you what you want for your standard deviation. It checks those outliers. Cool. So you run. Oh wait, let me double check. I didn't do all this. You do plots. This is for homoscedasticity. You put in your Z residual right at the Y part. You put your Z predictor in the X part. You want to check this part off for your normal probability plot. If you want a histogram, go ahead and check that off. And continue. Save standardized predicted values. You definitely want to save these distances because they might ask about that. Mahalanobis distance. is the one for multivariate outliers. Cook's distance is for univariate outliers. And you want to save your studentized residuals and your DF betas. I didn't save that when I did the count, but I think you guys said, Dr. G liked that. So since you're familiar with it, I left it on there. Options, nothing to worry about there. And you're all good. So you hit OK. All right. So first thing you do is you want to check for, I didn't unsplit the file. See, this is good. Good learning for you people. I was testing to see if anybody noticed it. You got a split file. You want to make sure you undo your split file. You hit reset. That's good, see? And then you have to redo it. Don't think you don't have to redo it.
Jacob, you're fired.
I was testing them. You hit OK. And just make sure you're looking at the right one now because you got 2 regressions up there. Cool. So is this one. Almost. Oh yeah, this is the one. Yeah, cool. So you check out your model summary table. You got your Durbin-Watson. So for this one, you want this one to be like between 1.5 to 2.5. So the closer to 2, the better for your Durbin-Watson. So you could say something like, for Durbin-Watson in this case, it wasn't quite so good. It was almost, it was right below that 1.5. So you could say something like the assumption of independence was not assumed as the Durbin-Watson statistic was below the cutoff range of 1.5 to 2.5, or too far away from 2. You would talk about how, you could talk about, let's see, residual statistics, where you get your Mahalanobis distance and Cook's distance. You want your Mahalanobis distance. It's used to detect multivariate outliers. The cutoff depends on how many predictors you have often. But you got your studentized, oh wait, no, where is it? Mahalanobis distance right here, and you got a minimum of 0.246 and a maximum of 12.830. And so you don't have to go into too many specifics about, you know, all these specifics that I have in the printout that I gave you guys, the handout. But it tells you exactly what the cutoffs are depending on your number of predictors. So here we have 4 total predictors, and the cutoff for that number is 13.277. So this one is right beneath that, so that's good for your maximum. And then you also have your Cook's distance, and that one should not be above 1. So we're good for Cook's distance as well. So you probably won't have to know all those specifics about those detailed numbers, but if you do, props to you. Then you got your linearity as well. This looks pretty linear. You could just mention the line graph and say it looks like according to the normal PP plot of regression of standardized residuals, there was the assumption of linearity was met, or however you want to word that. And then this is for homoscedasticity. This is where we put the Z predict over the Z residual. And you want this to look kind of like a nested design. It's like this is really one of those visual ones. They'll be happy if you mention this one. You just talk about how it's nested and appears to meet the assumption of homoscedasticity. If there appears to be some kind of, if it's not nested and there appears to be dots here, dots there, you would say it roughly appeared to have violated that assumption. But they'll just want to hear that you mention it and know a good bit about it. Now, let's talk about what we found. So the first thing you look at is your model summary again, and you would want to say, according to the model summary table, there was an R of 0.651. And then you could also say the R square was 0.424, indicating that 42.4% of the variance was accounted for by the by each of the predictors that were plugged into it. And then you go down to and the specifics about how to write that out is listed on the document. And then you talk about the regression and residual. So here, this is just a test to tell you if there was significance or not. So then you could say according to the ANOVA table for the regression model, it would appear that the data was significant. You put the F, you put the degrees of freedom for your regression residual, and the significance P less than 0.001. Here, you might want to add this to the assumptions, which I just forgot. You got your tolerance and your VIF, because you also want to talk about multicollinearity when you're looking at your multiple regression. So once you're writing out that bottom part, you go back up to the top part and write out this, or you can just write it first if you remember it while you're taking your test. And you put tolerance, you want tolerance to be high, you want your VIF to be low. You only have to report one of these. I would just report the tolerance, and I would say something here like, you know, these were kind of low. The tolerances are low. You want them to be closer to like 0.7. So you could say something like according to the coefficients table, the variables were not very tolerant to multicollinearity, with tolerance levels being below 0.514 for each of the variables. You can mention each of these, whatever you're comfortable with, but you only mention one of these, and you just say
Alexa?
tolerant or not. Huh?
Sorry.
Oh, you good. Lastly, you want to talk about where the significance was, what contributed the most. So here, once you're going through your analysis, if you go down to page 28, this is a good example of how to write this out. So you would say something like, according to the coefficients table, the predictor variable of, well, first you want to see which ones were significant. So it looks like none of these were significant. So you would say something like, there would appear to be no significant predictors according to the coefficients table. And you would just say with, but then you could go on to say which ones still contribute the most variance if you want to be safe and you have time. You would go on to say that according to the coefficients table, it would appear that the all feelings of being ignored was the most significant predictor of whatever your outcome is, tossed or no toss, I think in your example. So you would just go to say this one, and then you would say how much it contributed uniquely. So you would say with a unique contribution of 0.171. So you go straight to that part correlation. And then after you mention your part correlation, you could then go on to square it so that you get your variance accounted for. So you would square this number, -1.71, and then you would say it accounted for so and so amount of variance. So that whole sentence is laid out there, just set up for you guys if you want to go back and see how to write it out. The last thing you can mention for this is, once you do find that one that's most significant, you could say something like, more specifically, all feelings of being ignored. For every 1 unit increase in all feelings of being ignored, there was a -0.969 decrease in whatever your outcome measure is. And you could say, while all other factors are being held constant. So that's an important sentence. I have that written out as well. And all the setup for how to write these things out. Okay. That is all the practice questions that I think are most important for the comp exam. You guys have 90% of it all recorded. If you have questions, again, go to Anna, Renee, and I from Now Between the Tests. You guys have also more examples at the bottom if you want to look at other t-tests and how to write those things out. You have other different types of ANOVAs that you can look at how to run. Our practice, making sure you're able to do these things in APA style and all that good stuff. Check out the videos if you have extra time, and then also spend some time reviewing those concepts related to the second part of the competency exam. But I think you guys have a lot of good resources, and don't hesitate to ask for more support. I think this was quick, but you got to record it. So, all right.